Good afternoon. Today in this class we'll study the next topic and the last topic of permutations and combinations, which is generating permutations and combinations. Generating permutations and combinations is basically, in all the previous classes we have studied about just counting the number of permutations and combinations we have for each problem. Okay, so we have generally studied about counting, but in this topic we will study why do we need to generate permutations and combinations and not just count. So consider the problem of a salesperson. If he is traveling 6 cities, okay, and for traveling 6 cities he can, the different permutations will be as follows. The first city can be chosen in 6 ways, the other in 5, 4, 3, 2 and 1 way. Now with respect to this, if we have the number of different ways of visiting the cities will be 6 factorial, which is equal to 720. Now, for each city we have, for visiting 6 cities, we have 720 ways. Now, which visiting will give us minimum amount of time? We have to calculate that. So to calculate that, a person has to know all the 720 ways, correct? So all the different kinds of permutation should be known to find the one which is giving us minimum amount of time. Similarly, with respect to combination also, we need to know the different combinations so that we know which problem will be the optimal. Optimal is basically, optimal solution means basically which gives either the maximal or minimal based upon a problem. Okay, so to know our optimal solution, we need to generate the permutation and combination. So we'll see simple examples. Here the method which we are studying for permutation and combination is lexicographic order or dictionary order. That is, if we want to study about the lexicographic order, if we have been given a set of number or alphabets, we want to know what is the next number or alphabet in the dictionary. So suppose if you have a dictionary with these number 1 2 3 4 5, okay, so how many total numbers you will have? You will have 5 factorial numbers. Okay, so 5 factorial is basically equivalent to 120. Okay, so totally you will have 120 permutations of this number 1 2 3 4 5. So the first one will be 1 2 3 4 5. Okay, the next number will be 1 3 2 4 5, and this will go on till we get all the 120 numbers. So in this case, if we have 2 3 4 1 5, what will be the next number in the dictionary? For 2 3 4 1 5, the next number in the dictionary, if we want to find out, we will take the lowest number from over here. So we have, after we will compare these two numbers. So 2 is less than 3, okay, 3 is less than 4, okay, 4 is less than 1, these two numbers are false. So we will keep 2 3 as it is, and with 4 1 5 we will check the number which is greater than 4, which is 5, and keep the next numbers 1 and 4 in the order which is the smallest. So it will be 2 3 5 1 4. So after 2 3 4 1 5 in the dictionary, the next number will be 2 3 5 1 4. So this is basically your lexicographic ordering. Similarly, for another number 41532, we will keep checking, is 4 less than 1? Yes, 4 is less than 1. So over here only the first position 4 will be replaced by the number which is greater than 4. So it will be replaced by 5. So we will have 5 first, and the next numbers should be arranged in an order which is the smallest. So after 5 we will keep 2 1 4 3. Okay, so the permutation for after 41532 we get 52143. Okay, we will also get 51234, 51243. Okay, so these are the numbers which will be in the dictionary order. Next, similarly, this is the method to understand it. It is basically an algorithm. Now we will see with a smaller example. 1 2 3, what are the different permutations that can be created? So with respect to that, So for this number 1, 2, 3, we have to generate the lexicographic order. So this is very simpler to understand. So 1, 2, 3, totally you will have 3 spaces to be filled. So for the first, we will have 3 choices, for the next 2 and 1. So 3 factorial ways, that is 6 numbers. So how can these 6 numbers be arranged in the dictionary order or the lexicographic order? 123 is the first number. The next number can be obtained by interchanging the 3 and 2. So we get 132. Next, because 3 is greater than 2 and 1 is less than 3, what we do is we put the smaller position of 3 and 2 and then we change the order. So we get 213. Okay. So basically what we are doing is we are changing this. We compare 1 with 3 and 2, which is the smaller number 2. So we put it in the first position and then we arrange the next two numbers in the least, that is among 13 and 31, whichever is smaller, we take that and arrange it. After that, we have 231 obviously, and then finally we will have 312 and then 321. So this is the order if we want to arrange it in the dictionary. And then lastly, the next topic is generating combination. So for generating combination, basically whenever we are talking about combination, combinations means just the set of numbers, subset of a given question. So combination is basically a subset of your given problem. So suppose if we have the question finding the next bit string after this number, then what we supposed to do is check from right, whichever number is not 1, to replace it with 1, and whatever next numbers are there, replace it with 0. So we have 1 0 0. The rest of this number will be as it is. So 1 0 0 0 1 0. This part is changed. That is, we check from right, change the number which is not 1 to 0, and the numbers after that to 0. Okay. So this is the generating combination. And lastly, with respect to the same problem, same combinations topic, if we want to find the next larger 4 combination, what we have studied with permutations, it is the same, but here we are taking the subset. So after 1, 2, 5, 6, what is the next number from this set? So after 1, 2, 5, 6, what can be the next combination, next larger 4 combination? So we can have 5, 6 is done. Then can we have 1, 2, 6, 5? Okay. Or else we can also have 1, 3, 4, 5. Any next larger combination is basically whenever we want to generate the next larger 4 combination of the set, that we have to see what will be the next larger number after this number. Okay, in the dictionary order. Next, we will be continuing with the next topic of our syllabus, which is proof strategy. That is, this is your unit 2, part 2. And first topic is proof strategy. For proof strategy, let's start with that. Whenever we are talking about proofs, if you remember, we used to have the implication and we were supposed to prove P implies Q. Now in this case, a proof is basically whenever a statement is to be proved, first replace the terms and then by their definition analyze what we are supposed to conclude. If a statement is a conditional statement, then try a direct proof. Okay, so if you have a conditional statement P implies Q, then direct proof is we have to prove that this is true, and if P is true and Q is false, then only false. All the other statements will be true. So this is your direct proof. And what about if it is not an conditional statement? Then we can have something known as indirect proof. And if both of these, direct proof and indirect proof, does not work, then we can also try proof by contradiction. What do you mean by proof by contradiction? That is, we have to prove that our hypothesis is false and our contradiction and our conclusion is also false. If both of them are false, then obviously our actual statement will be true. So this is basically your P implies Q. True, true will result in true, but if your hypothesis is true and conclusion is false, this statement will be false. Then after that, if one of them is false and true, and if both of them are false, then also it will be true. So this is your proof by contradiction. Now whenever you're supposed to take the proof strategy, we have two types of reasoning. We can perform either forward reasoning or backward reasoning. Forward reasoning is basically whenever we are choosing a method, we need a starting point. Okay. To begin our reasoning, we begin by direct proof for a conditional statement, and we start with the premise, which is your P. And using this premise, we create a proof by using axioms. If you remember, I have given you the definition of axioms, and then we use a theorem. Okay, and a proof can be constructed by using your sequence of steps. So if we have a hypothesis or a premise P, we use some theorems which are already existing, and then it leads to the conclusion. This type of reasoning is called forward reasoning, and this is the most common type of reasoning used. Okay, apart from that, we also have backward reasoning. So forward reasoning is usually difficult. So for that cases, we use backward reasoning. And now, if we are using our forward reasoning or backward reasoning, I have said that we will be using theorems. For theorems to be used, what are theorems basically? Theorems are basically something which is known as an existing proof. They already exist. We can take a theorem, and with the help of it, we can create our conclusion. We can prove that our conclusion is true. Often an existing proof can be adapted to prove other facts. Now looking for counter examples, suppose what did I say about proof by contradiction? If we are saying 2 square is 4, okay, so what we are supposed to do in the case of proof by contradiction, we are supposed to prove that every other square, every other numbers a square. So 1 square won't give us 4, 3 square won't give us 4, and so on. So we have to prove that all the other square of numbers won't give 4 except for 2 square. So this is your proof by contradiction. Okay, so based on this, we can perform a few examples. Let's see the example. So for backward reasoning, a very important problem is, suppose if we are given two positive numbers which are real numbers. Okay, so positive real numbers x and y, and there, if you remember, arithmetic mean of two numbers will be x plus y by 2, while their geometric mean will be root of xy. Then we have to prove that always arithmetic mean will be greater than your geometric mean. So for this, how can we prove this? We are starting with our proof x plus y by 2 is greater than root of xy. We have to prove this. So let's consider that this is true. Okay, if this is true, we can consider that x plus y square by 2 square is also greater than xy. Okay, and then x plus y whole square is greater than 4xy, and this can be expanded as x square plus 2xy plus y square is greater than 4xy. Okay, we are considering this entire statement as true. Consider it true. Okay, now x square minus 2xy plus y square is greater than 0. Now this can be replaced with the formula x minus y whole square is greater than 0. If we know that anytime we are taking a square of a number, it will always be greater than 0. So this is true whenever x is not equal to y. If it is becoming equal to y, then it will become 0, obviously. So this is true whenever x is not equal to y. So if this statement is true, then it means that this statement is also true. Okay, so this is the backward reasoning. Okay, we are considering the conclusion statement to be true and then considering that our premise is also true. And apart from that, we have another topic which is tiling. So in tiling, we will study about something known as a checkerboard. So checkerboard is basically a rectangle divided into squares of the same size by horizontal and vertical line. So we consider horizontal and vertical line. So basically your checkerboard will be in this fashion. So over here we have it divided. So checkerboard is very similar to a chessboard. So in this case, what we are supposed to do is, how can we color this checkerboard in such a way that whenever we are talking about a standard checkerboard, it contains 8 rows and 8 columns, and we are supposed to tile it. And how are we supposed to tile it? We are placing dominoes. So dominoes is basically a rectangular piece, okay, and we are placing it on this checkerboard which has 8 rows and 8 columns. If you check it, so this is your standard checkerboard. Now in this case, how can we style the standard checkerboard using dominoes, or how many tiles, how many dominoes do we require? So basically, if we are taking a domino, it is a rectangular piece. It is in this fashion. It is created by using 2 tiles. So whenever you overlap it, it will occur on 2 tiles. So let's just, so if you put this domino on your checkerboard, it will be placed on 2 squares, okay. And how many such dominoes should be placed on the checkerboard that your standard checkerboard is completely filled with dominoes? So if you say, if we have over here 8 rows, 1 2 3 4 5 6 7 8, similarly 8 columns, so it is 64, and dominoes is always placed on 2 tiles, so it will be 32. Similarly, with respect to this, we can get different kind of problem. That is, if we are cutting the corners of the checkerboard, if we are, I'm not considering these 4 squares of the checkerboard, then how many tiles will be required? Then we will require only 30 tiles, okay. So in this way, we will get various problems which can be solved easily, because it is more of a logical problem than something which requires explanation, okay. So this completes the topic proof strategy. After that, we have sequence and summation. So what do you mean by a sequence? A sequence is a ordered list of elements while, so if you have a sequence with a few terms, then suppose if I'm talking about the sequence of odd numbers, so we will have 1 3 5 7 9 etc. And similarly, if we are talking about an infinite sequence, okay. So if you define a sequence in formally, it will be a sequence is a function from a subset. So it is an ordered list of elements like a set, but elements, we can have duplicate elements, and elements are ordered. The difference between sequence and set is as follows. Now we have the formal definition. A sequence is a function from a subset of Z to a set S. Okay, so from integers to a set S, and usually from the positive or non-negative integers, and an is the image of n. What do you mean by an? An is a number in your sequence, and when you are writing an in brackets, it means your entire sequence. So the same notation as sets. Now let's see an example of the sequence. An is equal to 3n. So whenever we are writing an is equal to 3n, a1 will be equal to 3 into 1, a2 will be equal to 3 into 2, a3 will be equal to 3 into 3. So the sequence is basically multiples of the value 3. 3 is 6, 9, then a4 will be equal to 12 and so on. So these are the numbers in the sequence. Now bn is 2 power n, so b1 will be 2 power 1, b2 is 2 square, and this go on. So basically this sequence is the powers of 2. So it is 2, 4, 8, 16, 32. And note that the sequences are indexed from 1. Okay, so whenever we are speaking about sequences, we are supposed to start it from 1. Sometimes we can also start it from 0. We have geometric versus arithmetic sequence. So a geometric sequence is basically whenever they are arithmetic sequences, whenever they are growing by a constant amount. So after 1 we get 2, 3, 4, that is incrementing by 1. Geometric sequence is basically when it is incrementing by more than the constant factor. So over here, instead of increasing by 1, they increase by the some factor value. So this is your arithmetic sequence. An is 3n, 3, 6, 9, 12. So geometric sequence, we keep adding the values. And in arithmetic sequences, we keep adding the values, while geometric sequences, they increment by some factor, that is powers of n. Okay. So 2, 4, 6, 8, 12. Over here, we have to multiply by 2 each time. So each number is twice the previous. So of the form AR power x. Okay, this is similar to your geometric progression and arithmetic progression that you have studied in your earlier classes. Next, we have one of the most important sequences in computer science, which is Fibonacci sequence. So this sequence is neither arithmetic nor geometric. So this is whenever we add the previous two terms, we get the next term. So the Fibonacci sequence, it starts with 0 and 1, and we keep on incrementing it. So let the sequences as follows. Usually it begins with 0 and 1, then we add these two terms, we get 1 again, then these two terms we get 2, 3, 2 plus 3 is 5, and this continues. Fibonacci sequence is a very, very important sequence in computer science. That is, it gives us this equation, the fn, which is this value. So in this case, f1 and f2 will be this 0 and 1. So f3 will be basically f1 plus f2. So here it can be represented as fn minus 1 plus fn minus 2. So this sequence is the Fibonacci sequence. And to get, suppose if we are using this formula, if we want f50, we will require f49 plus f48. So we have to go on finding till f49 and 48. Instead of that, we can even use this formula. We will see the explanation of this formula in unit 3. So for now, if we want to find f50, what can be done is you have to just substitute n value over here. So it is actually written as 1 plus root 5 whole power n minus 1 minus root 5 whole power n by 5 into root 5 into 2 power n. In all these cases, substitute 50 and you will get easily, rather than finding till f49 and f48. So this is, you may have already studied the program. So determining the sequence formula, given values in a sequence, how do you determine the formula? So first and foremost, you are supposed to consider whether it is an arithmetic progression or geometric progression. That is it increasing by adding some value, or is it increasing by taking the powers of some value? Okay, so is it arithmetic or geometric, and does it have a repetition in the cycle, and does it combine the previous terms, or are there some values which are the same? Okay, we have to consider all these questions and then find the. So in this sequence, let's take this sequence. So this sequence is of alternate ones and zeros. Over here we have 1 and then 0, then 2 ones, 2 zeros, 3 ones, 3 zeros. So here we will have 4 ones and then 4 zeros, and it keeps on increasing the number of ones and zeros each time. Similarly, the sequence alternates ones and zeros, increasing the numbers of ones and zeros each time. And over here we have 1, 2, 2, 3, 4, 4, 5, 5. So this sequence is increasing by 1 and the next number is being repeated. So here 1 is being written once, 2 twice, 3 once again, 4 twice. So if you notice, these are even numbers being repeated twice, while the odd numbers are being written once, and we are keeping on increasing the value. Another is this one. So 1 0 2 0 4 0. So over here the 0 is basically representing the, if you take 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, these numbers represent the powers of 2, while we are separating these numbers by adding a 0 in between. Okay. So the non-zero numbers are a geometric sequence 2 power 2 power n interspersed with zeros. That is, in the middle we have entered zeros. Now what about this? 3, 6, 12, 24. So over here, this is 3. Okay. Then 6 can be written as 3 into 2. 12 can be written as 6 into 2. So each number is being multiplied by 2. This is a geometric progression. Okay. Each term is twice the previous geometric progression, and it can be written as an is equal to 3 into 2 power n minus 1. So a1 will be 3 into 2 power 0, a2 is 3 into 2 power 1, and it continues. So it is increasing by powers of 2. Similarly, if we want to determine the sequence formula, after 15 we have 8, after 8 we have 1. If we observe, between 15 and 8 the difference is 7, and between 8 and 1 the difference is 7. So this is basically, each time we are decreasing the number by 7. Each term is less than the previous term. Similarly, you can solve for the following. 3, 5, 8, the difference between successive term is increasing by 1. So between 3 and 5 we have the difference 2. Between 5 and 8 the difference is 3, and so on. We can use these formulas. So these are the example problems. And few of the useful sequences are n square, n cube, n power 4, 2 power n, 3 power n, and factorial. Okay, so these are the useful sequences to be remembered. And this concludes the topic sequences.